probably are all involved in a way or in another, into attentional process. And that, I think, maybe it would be interesting to compare this kind of experiments in image studies to see how we can pick up some frontal activities, or if it's not possible. Thank you.
Thank you for your presentation, but what I want to know is perhaps a general question of the technique you are using by subtracting two waves from each other and making maps of the difference. Mm-hmm. I mean, is this real physiological data that we are looking at?
Sorry, if it's physiological data?
Yes, is it from real sources? Because if you have a slight shift in the waves, a slight shift in the peaks, you're subtracting things that are not real physical data, I think. I mean, you find a wave and you can make a map of it, but is it a real thing happening in the brain? Is
yes.
It not something that you are making because you are subtracting just two things that you... I wonder if you are allowed to do that. That's what I want to ask you, or perhaps a scientist here that knows everything about that.
What I can give my answer, but if people have other answer, I'm glad to hear also. That is a very common way to do in many studies about cognitive. I agree that maybe it's not the right way to do. You can also, there is a problem of jitter, but that is even the problem when you make not only a grand average between subjects, but even when you sum inside the same subject, the technique of evoke potential, you make the same, in fact. You can mix some jitter, and what you pick, what you record is a kind of resulting activity, statistical resulting. And yes, I continue just a bit. These results, I agree that if I observe this kind of results in only one subject or only one time, I will say absolutely nothing about that, because the current scalp currents have other disagreement to be sensitive to noise, so it could be quite add some arguments to yours. But the fact that it's very stable in time, in space, in patients, in experimental conditions, mean that probably there is something of this kind of type which happens. It doesn't mean it is the reality.
Let me just add one.
If you look at the P3, and if you do the P300 paradigm, and you look at only the N100, you see that most of the time the N100 in the target is quicker, is faster than in the non-target. Mm-hmm. And I think the source of both target and non-target N100 is the same. But if you would subtract this, you get something which is different. You
yes.
don't get the same source. So you get a wave or a map that is something representing something else.
Maybe.
That's what I mean.
What you try to do is to subtract curves which are, but that is a problem, really very hard problem, if not impossible. We try to subtract curves which are recorded in the same, absolutely same physical stimuli. That is, we never subtract, yeah, of course, we subtract deviant from a standard for the mismatch negativity. But we do that with mismatch, with deviant very close to the standard in frequency band, the most close possible to try to have the best, the less difference possible. And you can read all the papers by Nathanen showing all these effects.
Can I use the chair as provided to intervene? There are usually I come very hard on the side of the speaking, but here I have to support the method on two counts. By using current density, you are filtering out things which very slowly, and therefore any differences which are not much accurately, they're going to disappear. Now, both the current density and the two effects are linear. Therefore, you're allowed to subtract, provided you're careful. If you come to interpret deep structures, for example, if you apply some kind of Gaussian smoothing and you try and interpret the results in terms of sources, then I would have a problem. But for those superficial sources, I think the kind of description is quite reliable. Simply because you filter out the slope components which are most likely to be different. Any other questions? I've got one more question. You have not extended the region to the P300s around 300–400 milliseconds. Is that deliberate?
I have one if you want to go.
I promise you, I didn't know that.
No? Continue. Continue. Yes, that is P300. Here is the potential distribution between 225 milliseconds and 300 milliseconds in potential. So yellow potential, a very high potential here, 28. And here is the associated scalp current density. And that is interesting because what we can see is that there is something relatively well shown here, which in fact continue to be present even at large latencies, but very weak compared to these maps. It's the same scale. The best definition scale by map, it means that you should have the same, well, it's a little difficult to explain, but given these potentials here and this distribution here, we should observe. If we don't observe anything here, when you have this big potential here, it means that there is a main source which is deep in the brain. But there remains something here frontal, which is maybe what people call P3A, which is cortical probably.
But this is the area where it would be dangerous to if there are deep sources like that, it's dangerous to interpret any difference, especially in the Laplacian. Any more questions? Right, I would like to thank all the speakers for some wonderful presentations, and thank you all for your patience. Thank you.
For the registration recording the electromyography, and in this point in the forearm for the recording the action potential of the nerve. We have also two ground, one for the muscle, another one for the nerve. In this position we have the nerve stimulation of the median nerve. Obviously, we record the cerebral somosensory evoked fields, typical 6 subsequent positionings for 45 scalp sites. Recording also for two molecules in the response, one channel somosensory evoked potential, and all subjects underwent to MRI for the localization, three-dimensional localization on the source. The results of this study show a very important fact that the response recording at a little the muscle and the nerve show an amplitude linearly related to increase the stimulus intensity, and for which it's possible to see the signal recorded. This is the electromyogram recorded on the musculus opponens pollice, and it's possible to see the three different conditions of stimulus. This one is the level A with any muscular response. But for the same, so the response is not so easy. And it has a very tail greater table plateau that is possible to see when we have a signal recording on the scale. This is the amplitude of the response at the three stimulus level. In this stimulus stamp, all intensity, and then have this B is conditional, only motor, and C is parameter. It's possible to see that there is significant increase between A stimulus and B stimulus, but not significant increase between B and C stimulus. Possible to see this condition also in a graph. Reporting this graph, we have response of the muscle with a nerve increase, response of the nerve also increase, and response of the sonosensory vocal field that you show at this plateau that you probably have saturation effect. This observed behavior suggests a saturation effect at only a cortical level. In order to find out whether or not this is a real effect, is not due to depending on the source or deepening. This picture shows at the azofield map representing on the scalp of the subject. This representation is fitted on an ellipsoid fit on the real head of the subject, and it's possible to see the field distribution at the latency about 20. For the third simulation, this is the supramaximal, and that we also an increase, but not significant, because the values is almost the same, at the same latency, about 20-21 milliseconds. And then we have performed to localize this pattern, and we have a clear a clear localization of the three components of this evoked potential. This is possible to see in this picture. And then it's possible to see that the equivalent source show a real shift, but no, don't go in deeper, and this is significant for two